Alright, hey guys, what's going on? So today we are going to be talking about torsion, and we're going to start talking about the Lie derivative. Also, we're going to spend a couple of videos talking about these very important concepts because they're going to show up later in this tensor calculus playlist. Make sure to hit that like and subscribe button if this is the kind of content you like, and make sure to go into my Patreon page if you want to support the channel as well. Anyways, let's get straight into the topic. So we're going to recall from the covariant, recall that the covariant derivative told us something about how a vector field deviated from this idea of parallelism. The idea that you have a vector at one point in space, and then as it traverses that space-time or the manifold, it can be parallel transported. In other words, some property of sameness is going to be preserved as it travels. And the covariant derivative is going to tell you how much it deviates from that preservation of sameness. And so we are now going to see that the covariant derivative is going to play a large role in formulating two important tensors, one being the torsion tensor, which is laid out right here, and the other one being the curvature tensor, which is laid out right here. Okay, so the curvature tensor is the common one that you see a lot. That's the Riemann Curvature Tensor. We're going to cover this quite a bit. But I want to cover the torsion tensor a little bit also, just to give us an idea of what to look forward to when we start trying to implement spin into the picture as well, which is going to be later. But anyways, so we have this torsion tensor, and it's made up of covariant derivatives, and this thing called the Lie derivative, which we're going to talk about. And then we're going to talk about the curvature tensor later. This is the Riemann curvature tensor, and it looks like this. And this is made up of covariant derivatives also, as well as the Lie derivative. So the Lie derivative and the covariant derivative are the essential ingredients to building these two very fundamental, I would argue, the most fundamental tensors when it comes to differential geometry and tensor calculus. Okay, so how are we going to picture these things? We're going to go about talking about these tensors by first talking about the when we talk about torsion, we want to sort of put this within a physical context, right? The idea here is that as we have some curve, and as some particle or some object traverses the curve, it has associated with it a frame, right? A frame of reference. That frame of reference, typically called the Frenet frame, is something that travels along with that particle on the curve. And that Frenet frame is defined by three orthogonal vectors. One of these vectors is going to be the tangent vector. That's going to represent the velocity of, or the change in position of that particle. And that's a tangent to the curve, because the tangent tells us something about how something is changing with respect to space, or with respect to time. This is all with respect to time. The n, the normal force, is going to be, this is the normal vector, and this is going to give us a sense of force, the force that this particle experiences as it travels along a curve. And then we have this third vector, which is going to play a role in torsion, which is going to be the binormal vector. And this binormal vector gives us a sense of torsion. How is this particle twisting as it traverses along a curve? And this idea of torsion, or twisting along a curvature or some curve, is going to play a huge role in spin later on, like I've mentioned, because spin, we found out that in the in my no-nonsense quantum field theory playlist. My apologies about the stuttering. I was blanking out there for a second. But we found out in the no-nonsense quantum field theory playlist early on that spin will rotate into each other. Okay, you go from upspin to downspin, and we found that out in an earlier video. You can go check that out if you want as well. So, and this is sort of the area of differential geometry, right? So we're going to start seeing a lot of overlap. Not a lot, but quite a bit of overlap between this playlist and the playlist I'm concurrently making as well every Mondays on visual differential geometry. These tensor calculus playlists, as you've caught on, hopefully by now, these are being released every Wednesdays and Fridays. But anyways, okay, so we have the tangent curve, we have the tangent vector, we have the normal vector, the binormal vector. We can look at these planes, right? So the tangent and the normal form a tangent plane, right? So that's going to be this tangent plane right here. I've labeled it. And then we have another type of plane that's formed with T and B, right? So T and B, these form a plane called the osculating plane. Not oscillating, but osculating plane. I've sort of mixed that up in the past as well. But this oscillating plane is going to tell something about the torsion. So this plane, this oscillating plane is actually going to oscillate around this particle as it moves, and the degree to which it's oscillating will tell us something about how. Will tell us something about the torsion of that particle, or the torsion that the particle experiences. All right. So here's how things are going to go down. Right. So we're going to not really start off with torsion. We're actually going to start off with talking about the Lie derivative. Then we're going to put that in the context of torsion freeness, and then we're going to put that in the context of torsion. So we're going to sort of work from the inside out and get to the concept of torsion. All right, so let's compare now a little bit more in depth the Lie derivative with the covariant derivative. So as we've seen in the past, the covariant derivative is going to tell us how the vector changes from parallel transporting. So we have some vector at point P, and it's going to travel to point Q along some dx, right, along some dx, some small change in space. And as it does that, it's going to deviate from its parallel counterpart at vector space located at Q. And so we're going to get a vector, and that vector is going to tell us something about what the difference is between the transported vector and the parallel transported vector. Okay. Likewise, the Lie derivative is going to tell us how a vector changes from parallel transport on a closed curve. So this picture here, it took me a while to sort of develop this picture, but I really like this picture because it sort of, I think, puts into perspective the idea of torsion. Suppose we start off at a point Q here, or a point P, and here's our point Q that our geodesic passes through. And the idea here is that as the particle travels in one direction, in the v direction, say. Actually, no, these are the v curves, right? These are the u curves. So if the particle were to travel in the u direction and then in the v direction, the oscillating plane it'll change to some degree because the particle could have spin, or there could be some. That is to say that there could be some change in that oscillating plane as we rotate, as we go this way and then this way. Or if the particle were to go this way, and then here, and then to this point up here, so it's going this way and then this way, well, there's going to be a difference once we get to that point Q. Okay, so here's our point Q. And that difference is going to tell us something about the difference in the orientation of that oscillating plane. This is how I like to sort of visualize it, if you will. Visualizing really takes us only to an extent, right? You can't take this picture for totally at literal value, but I really like this picture because you can get a sense of how things are actually rotating with this picture. And so this difference here, you can imagine the oscillating plane rotating around, having sort of this distance to rotate around. Or it's rotating around the geodesic, and this distance sort of defines you could say the diameter or the radius of the difference between the orientations Q, right? So we have a point here, say, this is that point Q going in one path, going in this path, and then I'll do a different color, say light green, going in that direction. Right, so the difference between this point and this point is going to tell us something about the rotation or the torsion that the particle is feeling or experiencing. Right, and so if the Lie derivative equals 0, so the Lie derivative is going to tell us something about the change in this change right here. So if this is 0, then there's going to be no change on the curve, and therefore the direction by which we travel, either in the green direction here or the brown direction, that's not going to matter. So that's to say that the Lie derivative, this is going to be a closed curve. So that's to say that this direction, traveling in U, isn't going to matter if we travel in U and then V, as opposed to if we travel in then V then U. These should be equal. So if we bring these two, we can bring these two guys to one side of the equation, right? So we bring this guy to the side of the equation, we get something that looks like this, right? V in U equals 0. This is the Lie derivative, right? The Lie derivative is right here. That's Lie derivative equals 0. So we could say, so what we're going to say here is that this is the Lie derivative, this is the covariant derivative. And remember, this tells us something about closure of the curve, and this tells us something about parallelism. Because again, the covariant derivatives tell us something about how things are covariantly, or how things are deviate from parallelism. This thing tells us how there's a deviation in closure. Okay. All right. So we're going to define the Lie derivative in this way. This is the Lie bracket. Okay. And the Lie bracket, it can be thought of like this. This is the derivative of V in the direction of U, and this is the derivative of U in the direction of V. Okay? And that's exactly what we were talking about when we were talking about this closure, right? So the change, if we were to go in one direction, as opposed to the change if we were to go into it in another direction. Okay? So the closure here, so the closure here, and then we have this parallelism. I sort of rewrote this already. Okay. If we bring this to this side of the equation, then we get something that looks like this, and we're going to define this whole thing to be the torsion. Okay, so this is the parallelism minus the Lie bracket is going to give us torsion. So if torsion equals 0, then we get this case. And if this equals 0, then we get the case in which this holds true. Right. So this is, we go back to this picture here. If the Lie derivative is 0, then we have something called torsion freeness. Right. So let's actually get back here. So actually, if this is 0, that's going to be, this is called torsion freeness. If this tensor, this is a torsion tensor, if this is 0, that's going to be torsion free. So this is the torsion free relationship. All right. And so under torsion freeness, we could set the Lie derivative equal to 0. And if the Lie derivative equals 0, then we get this case. Right. So these are two constraints: torsion freeness and closure. Okay. If we're torsion free, then if we're torsion free and we're closed, then the direction by which we travel doesn't matter. If we're torsion free and we're not closed, then the direction still matters. Okay. But anyways, we have now this tensor. We have this tensor. Now we can figure out exactly what the components of this tensor are if we just fill in everything here, right? So the this is we've sort of talked about this before. This is the definition of the covariant derivative. This is, again, definition of covariant derivative. We're just doing for these two guys. And then this here is the Lie bracket. Okay. And then we have this, all this out here, right? So we have this all stayed the same. We're just expanding these guys, right? The derivative of this, we use the product rule, and we get this. Same thing here. These two guys are going to cancel, as you can see. And we can FOIL this guy out to get this, FOIL right here to get this. And then we have this here left over. So this and this, this and this. All right. So now we can see that this and this cancel, this and this cancel, and we're left with these two guys right here. I'll just erase. I'm going to erase these. I don't want any confusion. All right. We're left with this now. You can sort of see where we're going here. If we've been exposed to the concept of torsion before, we can factor out these guys, right? If we just change up some dummy indices on these right here, we just swap these two guys. It means we could swap these, and when we swap these, we can bring everything out like this. And then we get this right here. And this is a vector, right? This is because it has a basis. And this is how we compute this here's how we compute the components of the torsion. So the torsion tensor components are going to be calculated through these guys. So if there's a difference between the symmetric along these bottom indices, if there's a difference in the connection here, then there's going to be torsion. If torsion equals 0, if T x I j equals 0, well, that means that T k I j, or not T, connection equals connection k j I. Right, so if torsion equals 0, then we get this relationship right here. This is a rank 2, 1, 2 tensor. So that means that we can actually feed this some objects. Right, so we have our tensor located at a point. This particle is experiencing some sort of torsion. It's spinning, right? And we can compute that now through the affine connection. And like we said, it's a 1, 2 tensor. So 1, 2 tensor. The reason it's a 1, 2 tensor, again, the reason it's a 1, 2 tensor, if we go back here, this is a tensor, we've said. Therefore, this is a tensor. These two guys transform as tensors. These guys, this is just really a vector, right? Because we have these guys are really just vectors. We have vectors minus vectors. It gives us a vector. So, and vectors transform as tensors. Vectors are just rank 1, 0 tensors. So this whole thing is a tensor. Okay? So we can feed this thing, say A mu D mu, and actually, no, wait. Right, we have to feed it B. Let's see here. Let's see. We feed this thing. Right, so this has components dk, dx, I, dxj. So we feed this guy kij. We can feed into it, say, two covectors, right? Two. If we have b, not covectors, or bi, d, I, and then say, actually I won't say b, I'll say a. Right, so a, I, di, and b, j, d, j. Okay, we feed those guys in and we're going to get tk ij ai bj, and we're going to get dxi di. That's one basis, and then we're going to get dxj dj. Right, these guys are just going to give us Kronecker deltas. We're going to be left with a dk. All right, so that's just going to be tk ij a I b j. That's the basis, right? These are the components. This is the basis. We'll say the components are C, that's the new vector, K, D, K. So this vector represents, say, if we're looking at this picture here, the vector that describes the difference in the path. Okay. So if there's torsion, then direction is going to matter. That's what we've been saying before. And this is that torsion tensor. The torsion tensor is computed by the difference between the Lie derivative and the covariant derivative in two different directions. But anyways, where I'm pushing 20 minutes here, this is usually how long my videos go. So in the next video, we're going to talk about the Lie derivative of a tensor. Okay, and after that, we're also going to be talking a little bit more about the more of an abstract way of thinking about the Lie derivative, and then we're going to get into the Riemann Curvature Tensor. But if you like this kind of content, again, make sure to hit that like and subscribe button, and we'll see you guys in the next video. Bye.